Okay, so let's begin. It's my pleasure to introduce our speaker, Leif Azzopardi. Um, he's an associate professor of the computer information science at the University of Strathclyde in Glasgow. I hope I pronounced it correctly. He leads the interactive information retrieval group, and his research focuses on examining the influence and impact of search technology on people and society, and is heavily underpinned by theory. And he's an active member of the IR community. He has worked on various aspects of information access, from language models to economic models, retrievability theory, and user simulations for interactive information retrieval. He has published over 150 articles and received multiple awards, including ACM CIIR Test of Time Award in 2018 and ACM CIIR 2020 Best Paper Award. Without further ado, I'd like to invite Leif to give his presentation on modeling and measuring information interactions.
Great, thanks, Hamid, and thanks for inviting me to UMass. It's lovely to be here, well, virtually. And so, as you mentioned, I'll be talking about modeling and measuring information interactions. So, some of the recent surveys have shown that sort of many adults are divided on how technology impacts the way they live their lives, right? So on one hand, they believe that technology has improved their quality of life, encourages them to be more creative. But at the same time, they believe that technology has become too distracting and makes them less productive. And so these sort of statistics from the Harris poll actually exemplify how the systems that we design, right, are creating and affecting people in positive and negative ways. And so it means that we have a responsibility to develop solutions that actually support and empower people to be more productive, creative, and innovative. And so that's why a central research question that's been guiding my research and my group's research is exactly what Hamid pointed out, is how do these information systems that we design influence and impact people, organizations, and society in general? So let's think of an example and consider these two search interfaces, right? On the left-hand side, we have the Bing interface with lots of news items and so forth, and then we have the sort of plain vanilla one on the right-hand side. You know, when we think about this one on the left-hand side, you know, will people be more distracted? Will they lose focus on their task? Will they complete their search task more effectively because of these different elements? Or will they be distracted, right? And, you know, will they sort of lose focus? And then if we scale up from just one person to millions of people, then what are the larger consequences of this? And what are the ramifications, you know, to organizations, right? So, you know, if I have an employee, do I really want them to be distracted by the latest election results, or do I want them to get on with what they're meant to be doing and finding relevant information? And so as system designers, we need to be very mindful and consider the implications of these different designs or different designs that we can present and how they may impact our end users. The vendors, you know, there's different web news portals here, and the businesses that they support, and of course, then the bottom line of the search engine itself. Now, I'm not saying whether this interface is right or wrong, or better than the other one, or better and worse. Clearly, there's pros and cons to both of these ones, but they create compromises and trade-offs that we need to consider, and we need to scrutinize them, in particular with respect to what our, say, company's mission statement is. And so this is where I believe we can sort of learn a lot from thinking about economics and thinking about how we can look at the economics of people's interactions with the systems they use. And this is because economics provides us with a whole array of tools and lenses which we can analyze and investigate the impact of technology at the very micro scale, as well as the sort of macro scale, right? Economics naturally deals with trade-offs and choices that people face when they have scarce resources. You have a limited amount of attention and under various constraints, like time. But invariably, our end user, the person we're designing the system for, wants to get the most out of the system for the least effort, subscribing to, Zipf's law. And so by taking this point of view of thinking about how the economics of information interactions, it's given me actually a lot more respect for our end users because it makes us explicitly consider the costs that we're imposing and the cost because of the costs they incur and the benefits that they will receive from what we are presenting them with, and then go off to measure that in practice. And so by developing these economic models of how people interact with the systems, we can understand, predict, and crucially explain how people behave and perform. Now, in the past, the focus on understanding people's behavior has largely lacked a theoretical basis. But there's been a number of different approaches in doing this, right? So many of the papers we see in information retrieval studies are largely observational and empirical. We basically, present two interfaces and then see what people do. If we have a system, we just look at we start looking at the data and see whether they click more or click less, right? On the other hand, we've had a lot of people develop conceptual models. So this one here is Ingerson and Javelin's information seeking and retrieval model, which is a sort of conceptual model about the different factors that could influence people's search, seeking, and work tasks. If we have lots of data, then we can start doing data-driven approaches where we simply can start looking at the data and aggregating that and see whether whatever we changes whatever metric that we're interested in to make a thing, and see whether the intervention leads to a positive outcome or a negative outcome, right? But we're still largely hypothesizing what we do is going to work and then trying it out, right? And so this is where I've been looking at trying to think about how we can use theory or mathematical models in order to try and make predictions about how people's behaviors will change given a change in the environment, like the cost of a query changing. So for instance, the cost of a query, if that increases, then this will result in people issuing less queries, but maybe compensating by examining more items per query. So how do people behave when they search? Hamid, how do they behave, buddy? Randomly?
Irrationally.
Rationally.
Irrationally.
Irrationally. Oh my goodness, Jeremy, you don't really respect our users for being very optimal, do you? When was the last time you went to you went to your favorite search engine and then went, I'm going to be as irrational as possible and just type in a random string of something? I mean, I'm pretty sure you probably walk out of the system and then type in your best guess of what's going to be good, right? You've got a PhD from like UMass on, you query language model, man. I'll work out the likelihood of this query being generated from this document, right? But yeah, so we have these different notions that maybe people act irrationally, or they're lazy, or they're putting in the least effort, or so forth, right? But there could be arguments to say that actually they're acting rationally given the information that they know, or at least they are trying to maximize the benefit they get from this system, right? And so there's been a whole bunch of studies looking at how people behave, sometimes badly and sometimes in good in good ways. Thank you, Jeremy, for your input there. Hamid was obviously too embarrassed. So, you know, we see things like people tend to pose short queries, and there was a lot of work to say, well, why are they typing in short queries? You know, they only examine a few documents. I mean, they're lazy. They don't even look deeper than the second page, and they give little feedback. I mean, there's not even any relevance feedback on pages anymore, right? And all the research in the lab that we've done has pointed to, you know, type in a longer query, you'll get better performance. Go deeper, you'll find more information. And if you give feedback to the system, it'll improve the query and thus improve the results. So why don't people go to this extra effort of giving us more information, right? And letting us look at more items or look at more items or provide feedback in different ways. Just as a side, it's sort of like, you know, there is like, you know, with conversational search, we're going, oh, well, people will give us longer queries. But actually sort of been talking to Hamid and some other researchers about, well, look at the interaction loops that we have in conversational search, that would actually give more feedback. But people don't like doing that. So will conversational search actually work? So are they just being savvy and weighing up the benefits and costs of their interactions? And that's why they type in shorter queries, examine fewer documents, and give less feedback, because it's just simply not worth their while. So in order to start thinking about these problems, right, we started to model a very sort of simplistic kind of scenario, right? So we have our user, and they'll issue queries to a system, and the system will then retrieve a set of documents, which is ranked, right? And then the user will browse these items and look at a certain number of items in that list. So we'll say that's a fixed number. And clearly by looking at those items, they get some value, they get some information gain, right? And they'll either stop because they've found enough, or they will continue searching and issue another query and repeat this process until they've reached the desired amount of gain. And so I only want to touch briefly on this, but we developed some economic models that will then formulate the gain that people accumulate from the number of queries they issue and the number of items they look at per document. But then they also have a cost function. Each of those queries that they issue comes at some cost. And then the looking at the items themselves also comes at a cost of looking at the item, but also some cost of inspecting the results snippet. And so we can, you know, we can formulate this as an objective to minimize the cost of inspection to obtain a certain amount of gain, and arrive at the following formulas, which you don't need to go into really any detail here. But what I would like to communicate here is that we can now model these interactions that people have with the search engines, which allow us to then make predictions about how users' behavior will change. And so the theory says that essentially, if the cost of querying goes down, then people will issue more queries. And as a result, they'll start to compensate by looking at less items per query. And now, you know, so we kind of see this with the intervention of, like, you know, query autocomplete. The cost of querying when typing out a query is a lot cheaper. Queries, people look at more queries, but in some sense, the queries are becoming more effective, and so people don't look at as many items. Oops. But similarly, if something like the snippet cost or assessment cost goes down, so, you know, if you're looking at, if you move from textual snippets to, say, thumbnails, so we move from text search to image search, then it's likely that this will result in a decrease in queries, but rather an increase in assessments, right? So when we're looking for image search, the cost of looking at those thumbnails is very cheap, right? But we tend to look at a lot more of those items as a result, right? And so we've done some empirical research about that. So just going back to these like different designs, you know, could it be that the cost of querying on this interface on the left here is actually increased just by a little bit? And because of that increase, because there's a cognitive load associated with looking at the images and the pictures and so forth, and they have to make a decision. Oh, do I click on this thing about the rugby or the Grand Canyon? Or do I type in my query? What was my query about anyway? Oh yeah, I was searching for, yeah, that's right. I was meant to be doing my work, right? What is the equals operator in Java? And so maybe this will then really change the number of queries that would be expressed to the system when it's like this compared to when it's maybe a plain vanilla one. Of course, I understand that this is on the right-hand side is maybe less engaging. And so now we might see that it may be only worthwhile to reduce the query volume if the click-throughs to these news articles and so forth would lead to greater revenue than the queries themselves through, say, advertising, for instance. Search satisfaction aside, right? So these economic models that we've been developing tend to be quite simple and abstracted, but they're representative of the key interactions that people have. And so already Jeremy's talked about like the idea that people are irrational. And yes, people do have certain cognitive biases that may limit their abilities, but essentially, when we start thinking about whether these models as an optimization model, right, we can add in different bounds to their rationality, but what we can produce from those is a series of testable and intuitive hypotheses, which allow us to provide a compact representation of what we understand or how people will behave and interact with our system. So this will then inform designers. So then we can say, should we be focusing on reducing the query cost, or should we be trying to improve performance? Where do we allocate our resources here? Or what can we do to manipulate and influence people's behaviors? Do we want them to issue more queries? Then we really should drive down the query cost, right? So it depends on, but now we have some reasoning because we know how people are going to adapt their behavior in response to the incentives and the costs that we are providing or creating. And so we've been looking at applying these in lots of different contexts and develop models that look at this. It's essentially the costs and benefits of things like when to select facets, when it's worthwhile giving feedback, right, whether to bookmark or refined, and so on and so forth. And there's some references there if you're interested. And we also have done a number of full-day courses on this at various conferences. So that's kind of like a brief introduction really to where I've been sort of pushing my work. And the focus of today's talk is on measuring the performance, right? So looking at how people's behavior, how we can use these models of interaction and encode them within a metric in order to measure the utility that people extract from their interactions. So I'll be going through this framework, the CIIR framework, about how we compute expected utility, and then showing how we can take these sort of economic models and use that. So assuming that people will act in a sort of rational manner and try and maximize their gain while they're interacting, and then how that leads to a new metric, and then apply that to measuring the utility of being SERPs, right? So how do we measure performance, right? Well, typically we think about doing this by computing the expected utility of a ranked list, right? Now, otherwise, you can think about the expected utility as the rate of gain. And so Russell and Paroli and Card, over 20 years ago, basically said that this is sort of the claim that people are kind of tending towards being rational. People will modify their behaviors and strategies, the way that they interact with the system in order to maximize that rate of gain, right? They won't try and go about using the system to sort of get worse performance out of it. On the other hand, the information systems that we develop, we're trying to evolve those to maximize the rate of gain, to give the person more valuable information per unit of cost for their interaction. And so that means the way that we evaluate systems or a strategy, so because the way I use a system affects how much I get, and the way the system delivers it affects how much I get, we can tell whether one of those, or whether a system or a strategy is more superior if it actually yields more valuable information per unit of cost. And so this is where the rate of gain or expected utility comes into play. Now, as it happens, there's this framework called the CWL framework, or CIIR framework. And what it does, it allows us to compute the expected utility by injecting in a user browsing model, the way that people interact with a ranked list. So let's just quickly go through this, so these mechanics, and so that you can understand how these everything sort of links together. So if we want to compute the expected utility of a ranked list, so here we have our items and they've been nicely laid out in front of the user for them to go through. We have to make some assumptions about how they go through this, right? But essentially, we assume that there's some weight associated with the user, or this weight is the probability that a user will look at this item, or this item, or this item, and so forth. And those weights will sum to 1. And then each of these items will provide the user with some type of gain, like the relevance of the item, which say 1 or 0 or what have you. And then we just simply multiply the weights by the gains and take the summation, and we get the expected utility. And this is kind of like, this is like, imagine these are little boxes, and the user with some probability, given WI, selects one of those boxes, right, given the WI, and then that's what they get, right? And so the expected utility of them doing that action is how we measure the value of a ranked list, right? So the question is, how do we get these weights, right? Well, how we get those weights it really depends, right? So the question is, first, which result list is better? Well, if the user just looks at the top 2 items, then then obviously the list on the left is better. But if they're willing to go to the 5th item, then the one on the right may be better, because they have now 2 relevant items over here and only 1 here for this kind of thing. So the expected utility of the user really depends on how they're likely to interact with this with these ranked lists. Are they willing to go deep? How many items are they willing to look at? Where is their main focus? Is it mainly on the top or on the bottom? And so Carteret was, sort of one of his papers starts talking about how basically a user browsing model underpins all metrics. And so the idea here is that now we have our ranked list with our items within it. Then there's different browsing models associated with different metrics. So with something like reciprocal rank, so you can imagine, our user Norbert, he would go, he just says, well, I'll just go to the first relevant item and then stop, right? But then we can think about, like, a very sort of tricky measure. So our user, say Ian, he says that I'll just go to the kth item and then stop, right? So here K is 5, and that's his stopping model. Whereas someone like, say, Alistair, he might think, well, actually, I think that people, he would then flip a coin with probability theta and then decide whether to continue to the next item if it comes up heads, but if it comes up tails, he would stop. And so these different sort of user models can then be encoded mathematically. So put more formally, then we have this, what we call a continuation probability, right? So with reciprocal rank, this continuation probability, or the probability of going to the next item, is 1 for Norbert until he reaches the first relevant item, and then he won't continue after that. So it becomes 0. So this is a conditional probability of continuing to the ith item, given that the user is already at I. And so this is this model on the right-hand side, a simple Markov model. Whereas, say for Ian, he's a precision at K kind of guy. He'll continue with probability of 1 until he reaches his 5th item, K, and then it's 0. Whereas for rank bias precision, so Alistair's model, he will continue by flipping a coin, and if theta comes up, he will continue. Otherwise, they'll stop and stop looking at items. And for pretty much all the metrics like time bias gain, discounted cumulative gain, average precision, we can create different continuation functions that represent the user continuing down the list or not. Some of these may be adaptive, depending on the costs that have been incurred, or it may be dependent upon the relevance that's been incurred, or both, right? So something like what's called the bejeweled player model considers both the cost and the benefits that's been received or incurred before deciding whether the person should continue or not. What's nice about the CIIR framework is that they have worked out that the continuation probability is actually proportional to the weight. And similarly, if you have the continuation probabilities, you can work out the weight associated with each item. And so for reciprocal rank, to give you an example, it's just the weight is 1 over K up until the first item. For precision, it's the same until K. And for rank bias precision, we get this 1 minus theta, and then theta to I minus 1, which is essentially I to the ith rank that for each rank, right? And so we get these different weighting functions directly from the continuation function, and the continuation function is really just an instantiation of saying whether someone will continue or not, thus their user browser model. So the different types of browser models, like I've sort of alerted to already, each of the different metrics that you may be familiar with or already know about, like discounted cumulative gain, the continuation function actually increases if you are at rank 1 and then you move to rank 2. If you're at rank 2, you're more likely, you have a higher probability of then moving to rank 3. And if you're at rank 3, you have a higher probability than previously, then moving to rank 4, and so on until you get to your kth point, in which case you stop. With inst, the probability of continuing, you're more likely to stop as you get closer to what they call target. And that's under this metric, they assume that you have some notion of the number of relevant items that you'd like to find during the process. And as you get closer to that target, you're more likely to stop, right? With average precision, it's a little bit strange, but the user continues until essentially wants to keep continuing until they find all the relevant items. Whereas a measure like time bias gain, so if you're not familiar with time bias gain, it was Mark Schmucker and Charlie Clark. I think they won best paper at CIIR, I believe, in Toronto for this work. And so that's about 2003, it's many years ago now. And what they said is that that basically when you read an item, then the longer the item is, the less likely you are to go on to the next item, right? Because longer documents take longer to consume. And like I mentioned, the Bejeweled model, which was published only a couple of years ago at CIIR, the idea here is that once you reach your target, you will stop. So if you get your T relevant items, you'll stop. Or alternatively, if you're only willing to spend so much resources, so you're only maybe willing to look at 5 items, but you want to find 2 relevant items. So whatever one is exceeded first or met, then you'll stop. right? And they also have some dynamic variants of this so that, you know, if you're not finding any relevant information, then you kind of reducing the amount you're willing to spend on that transaction. And then thus you'll give up sooner. So what the CIIR framework allows us to do as a recap, it says that this continuation function, or this probability of continuing, completely defines the metric. Because if we have this continuation function, we can work out the weights. If we have the weights, we can then work out the expected utility of that list to us. Now the question is, well, how do we build a continuation function that encodes this economic model of search? Thinking if we had a rational economic kind of Homo economicus kind of user, how would then they go and search through the results? You know, clearly we're all not just Ians who have a precision P at 5 or a P at 5 or precision at 5 kind of user model. Always look at 5 items, regardless of whether it's relevant or not, and then stop. Nor do we sit around tossing a coin like Alistair to decide whether they look at the next item. And nor can we necessarily say that we're probably like Norbert, who says, I'm just going to look for the first relevant item and then stop, right? So, you know, so how can we make this sort of economic model of a user that is kind of adaptive and will change in response to what's actually being presented in front of them? So this is where we sort of turn our attention to information foraging theory. And this is another kind of economic model of search, but it's derived from behavioral ecology or optimal foraging theory. And it was proposed in Paroli and Card, and it's essentially equivalent to the search economic model that I presented. And we show the mathematical equivalence in some papers, but this one's easier for some analogy. So if you don't know about information foraging theory, it's like this diagram suggests, is that we as humans revert back to our primal forms in our hunt for information, right? And as it happens, animals tend to be fairly rational, fairly optimal, maybe not rational, but fairly optimal in the way that they forage for food and make decisions. So to start off with a sort of high level analogy, we can think about the sort of patch model, which is based loosely around this idea of the berry picker or Marcia Bates's berry picker, right? And the patch model basically tries to predict how long a user will spend picking berries. You know, we have these lovely, juicy strawberries, and we have these not so good, not ripe blackberry things here. And so how long should they spend in this patch before, or assessing the items and consuming them, before moving to a new patch, and then so on and so forth. So essentially we have this sort of between patch time and then within patch time. So getting to a patch is kind of like querying, and then staying in a patch is kind of like assessing. And so from this model, we have a number of considerations, or it's assumed that the forager has a number of considerations. They want to have a certain rate of gain. And the idea here is that, like, whether the ratio of the gain makes it worthwhile staying. So is it worthwhile me staying in here, or is the rate of gain I'm experiencing, like for each new berry I find, it's kind of maybe taking longer. Do I expect that I could go somewhere else and find berries more easily, right? And thus, if I could do that, I should probably switch and then go there, because I now can find berries faster, right? If you've ever played any online MOBAs like League of Legends or Dota 2, then you'll know how important it is to decide whether you should, you know, farm jungle creeps or stay in the lane or move to get kills, because you're trying to maximize your gold per minute. You're trying to maximize your experience per minute. And then, of course, they say that the forager has some certain requirements. They need a certain amount of gain. Like, you know, if we're animals, we want to eat a certain amount of food. We need a certain amount of calorie intake. But as infovores, you know, we consume information. And so we have an idea about how much information we need for a particular task or what have you. And of course, then we have constraints in our process. We only have a certain amount of time to forage or look through results. And so these are our sort of the three primary constraints considered. Now, so the idea of how long a person should then spend in a particular patch was kind of, or the solution to this was proposed by Charnov with his marginal value theorem. And basically it said that a forager should remain in a patch so long as the sort of slope of the gain function, right, or the rate of gain is greater than the average rate of gain in the environment. So as long as you're in a patch where you're getting more than you'd expect to get elsewhere, you should stay. And if it's lower than that, you should just bail, right? You just cut your losses, leave, and go somewhere else and start getting a better yield. So basically it boils down to something like these graphs. So imagine, I don't know whether this works. So imagine we have our sort of this part here is like the querying time or the time to move to a new patch. And this is how long I spend assessing the items. And if this is the average rate of gain, then Charnov basically says I should stop here and then move to another patch, right? Oops. So if this is my average rate of gain, then if I come to a patch which has very low yield in the next graph, right, then I should stop here. I should stop early and bail. But if I have a high yielding patch, then I should stop here and bail now, right? Basically the amount of time I'm spending is adaptive and it's based on how much I'm yielding and whether that's you know, above or below what I would otherwise get somewhere else. So the way that we sort of try to encode this idea or this notion within the information-based metric is to then decide how do we put them into the continuation function. So we then defined two sort of parts to this continuation function. One was this goal sensitivity. We said, okay, once you've reached your target, then you should stop, right? And so that's your goal sensitivity. I can only eat so much information, consume so much information. And I also have some idea of the rate of gain that I'm expecting. Now, you know, obviously people don't go around and going, oh, you know, this is how much rate of gain I expect to get from the system. But intuitively, over your interactions with your favorite or less favorite or alternative search engines, right, then you start to amass some idea of how often and how likely it is to pay out, right, and how much you're likely to get for different queries. And if it's falling below what you'd kind of expect, it's kind of like a dud query. You might go, well, maybe I'll reformulate. So we have this T that's related to our goal sensitivity, and we have our A, or average rate of gain, that we would expect for our rate sensitivity. And once we have those two probabilities, we can then combine them together, where we assume that they're independent, to formulate our final continuation probability. So, you know, if my goal is met, right, then my continuation probability would be like 0, in which case I will stop, because when you multiply those out. So let's see how we implemented these. And this is where we actually started to consider that maybe people aren't completely rational, right? And there's a because of this uncertainty within the environment. So we have this sort of function down the bottom here, which encodes the target t and this r parameter, which we kind of call loosely rationality. And so what it basically looks like is that we can set this function so that the continuation probability is a constant. So regardless of how much gain I have got so far and the target, I will just simply flip a coin randomly, right? But as I tune or change these parameters, right, if I set R to be very, very high, right, then it basically says I will always continue until I reach my target. And once I've reached it, I will stop. And so this is like, you know, that means the user must be 100% certain that they've reached their target, right? And know everything about that environment. In practice, Paul and I in particular debated this and said, well, actually, they're unlikely to really know when they've got their target. Maybe they'll get a little bit more, maybe they're willing to accept a little bit less. And so if you set this R parameter between 0 and infinity, infinite number, right, then what you get is this kind of curve shape, which says, as I kind of get closer to this target that I'm looking for, I'm more likely to stop or less likely to continue. And once I've met that target or exceeded it with the gain so far, I'm more likely to stop, to the point where, you know, once I sort of, you know, get a lot of gain or exceed my target by so much, I'm almost close to 0 in terms of continuing with the probability. Now, similarly with our rate sensitivity, we had the same notion because we thought, well, you know, sometimes, you know, you might look at the first item and it doesn't meet your tolerated rate of gain because it's not relevant, right? But if you're agnostic to the rate of gain, then this R2 would be 0 in this function, and we get this sort of, you know, it wouldn't matter what your current rate of gain is, and it doesn't matter what your tolerated rate of gain is. You just flip a coin. Conversely, if your rate of gain is not being met when you set this R2 to a very large number, then it says that if you're not getting that rate of gain that you expect, then you will stop. But when you're in the middle somewhere, it says that, well, maybe there is some chance you'll continue, right? If the rate of gain that you're experiencing is less than your tolerated rate of gain. So where, hopefully you can see my mouse cursor. And if you're exceeding that rate of gain, then you're much more likely to continue. And so now what it allows us to do is to sort of vary this R depending on how, you know, how uber rational people are, or whether just completely agnostic to the rate of gain or the amount of gain that they would like. So given these continuation functions, we can actually to define more the relationship between other metrics given these. And so by setting the parameters in different ways, so for instance, if I set the rationality to a very large number and the t to 1 in this C1 function, then I basically get reciprocal rank and then set when I set C2 to 1. And similarly with rank bias precision, I can set the R1 and R2 to equal 0 such that theta is now a combination of these parameters. And so what we can see is that the information foraging kind of metric can be pushed across the space to actually map out to these different other metrics. Now, precision is a little bit different because precision is a sort of cost-sensitive approach. And so in order to encode precision, we would have to encode another C function, C3, let the first two equal 1, and then use C3 to represent some type of cost sensitivity by using a similar parameterization. And so then, you know, so once we do that, imagine we had this third function, when we multiplied them all together, then something like reciprocal rank then would look like the continuation functions would be stop when you get to t equals 1, but it wouldn't care about the rate, and it doesn't care about the cost that you incur. Rank bias precision is agnostic across all three fronts, so it doesn't care about how much gain you get or the rate of gain or the cost. You just keep flipping a coin until you lose and then stop. And then with precision, you don't care about how much you get and you don't care about your rate of gain, but you do care about the amount that you're willing to spend or your budget. And so we can actually plot these out for like most of the most common metrics to see the spectrum, like I said. So what we've got here is we've connected the models of search behavior with measuring performance to create a theoretically underpinned metric using information foraging theory. But I guess now the question is, how well does this perform in practice, right? So I'm mindful that we're kind of running out of time. So I don't know whether Hamid Allah is going to allow me 5 more minutes because we started a little bit late, but otherwise I can do it in 5 minutes. Hamid.
I'd like to listen to this, but we have like back-to-back meetings right after this.
Okay.
Um,
So I'll give you the upshot here is, so basically we did this analysis on the Bing search pages, right? It's actually very difficult to measure search pages. So we had to do a lot of different things, but in terms of practical considerations to get the elements and the cost of elements out and stuff like that. But what's nice from the framework is that we can measure not just the, so I'll skip over the sort of methods and say, well, does the information foraging theory, I mean, you can look at the paper to see the methodology about how we actually did the measurements. Does it actually work in practice? And what's kind of interesting is that when we use these older metrics, they are not as accurate in predicting how much gain that people get. So this is the mean average error of the gain, the mean average error of the cost and the depth, like how far people go to. Whereas the current metrics that they use are fairly decent, but the information foraging metrics with some simple parameterizations actually is more effective at predicting how much gain people get, the cost, and the depth. So it's a lot more accurate. So that's kind of the upshot. So I'll just conclude then about going forward with like these economics of interactions, right? So clearly, like, you know, developing these metrics or putting this economic user into them things still requires more validation and analysis in terms of does it actually match up with user satisfaction. It does allow us to predict the costs and gains better. It also allows us to gives us a way to analyze different queries. So like I talked about these different goal, cost, and rate sensitivities, now we can then explore the queries and the users that we have to see whether they are more rate sensitive, cost sensitive, or goal sensitive, which should give us better insights into user expectations. And it has the potential to bridge this divide between online and offline metrics because we're able to use the framework, which I didn't go into details in, but we can use the framework to predict how long people would spend on a page and how far they'll go and spend on a page. And that means these are observables, which we would then see in practice. Of course, going forward, you know, we can measure sessions. We can look at measuring actual pages themselves if we have some continuation probability of how people go through items, go through the documents, or even streams with the framework to work out the expected utility there. And what we've been thinking about more recently is applying these kind of metrics to conversational search. And as we talked about earlier with Jeremy, you know, people aren't necessarily always rational. And so what we'd like to start thinking about is in particular how all these different cognitive biases affect people's interactions, and how we can encode these using something like prospect theory to make more appropriate models of user behavior that encodes Jeremy's irrationality. So thank you for this. Thank you for the opportunity to talk. Here's just the summary slide of the presentation.
Thanks, Leif. It was very interesting and complete presentation. I really enjoyed listening to you. And so we are kind of on time, but let's spend about 5 minutes for questions. And so if you have any question, just you can unmute yourself and speak up, or you can write in the chat and I can read it for you. Any questions?
So this is a really dumb question. But, what you're talking about is independent of what the underlying search engine has actually optimized for. Is that correct? Like, so if, let's suppose that the underlying search engine has learned to rank based on optimizing in DCG at 3, you're still the framework you're discussing is independent of that, right? Because a user might see that and decide to switch away from that search engine or switch away from that query because it's been optimized that way. Is that a correct understanding?
Yeah, that's quite possible, right? So like DCG is making an assumption that all users act in a particular way, right? The information foraging based metric we developed said that users will adapt their behavior depending on what they see and depending on the relevance and depending on the costs of the items that you put in front of them, right? DCG says it doesn't care that like the first item on the search engine result page could be a big entity card, and that takes some time to get past, and then they might put 3 ads, and then they might do something else, right? And so DCG is agnostic of the costs that you've imposed upon a person, right? They just assume that every element is the same. Within the information foraging metric we have, it's basically implicitly considering the cost because the rate of gain is expressed as the amount of good stuff I'm getting per unit of time, right? And thus, if I'm getting, if my rate of gain is lower than what I expect, I go, I'm out. Like, you've just served me up stuff, and I'm not willing to have this rate of gain. Yeah. So and that's why I'm saying, like, so for certain queries, those parameters within the IFT metric may be different, because for certain queries, like Facebook, right? If someone typed in Facebook, then they don't want to look through 10 things to get to the Facebook link, right? They want it straight away. Whereas for other queries, like, if they're looking for cheap flights, then they're maybe more tolerant of looking through lots of different things. So they're less cost sensitive, but they're more gain sensitive, right?
Okay, there is a question in the chat from Abdul Aziz. They asked that there are many search algorithms, including hits, that are based on hypotheses. Why? And what is the role of hypotheses in terms of satisfying the queries based on such a reinforcing relationship?
I think that's a very good question for Kleinberg. I think he's the one who did hits, right? I'm not sure I really understand the question. Can you help me there, Hamid, or?
Me neither. So, Abdul Aziz, would you please unmute yourself and explain what did you mean?
Oh yes, can you hear me?
Yep.
Yeah, there are so many algorithms, including HITS is also a search algorithm. Those are searching algorithms are basically uses or hypotheses. Like if you use HITS algorithm, that algorithm uses the basic two hypotheses, like how a good 30 page is linked to many good hub pages,
Yeah.
and the other hypothesis you can say how a hub page that can be a good one that points to many good other authority pages. So
Mhm.
I usually think about the search algorithms. Mostly the algorithms are using the hypothesis kind of things.
Mhm.
So why we are what is the role of that hypothesis, and we can see mutual reinforcing relationship between the queries, because hypothesis is similarly like mutually reinforcing relationship between the hub and the authority page.
Yeah, so I would interpret your idea of hypotheses as user models, right? So within HITS, you have this sort of random surfer user model where, you know, the person's randomly going around the web and then they keep ending up at certain hubs or certain authorities, right? Yeah. So I would have to think a little bit about like what you mean by reinforcing relationships. So I have to
Yeah,
keep
thanks.
thinking.
Yeah, yeah, sure, thanks.
Okay, so I think we're over time. So let's thank our speaker once more. And again, thank you, Leif, for accepting our invitation. And a few things is that we upload our recorded presentations to our YouTube channel. If you want to listen to our previous talks from Grace Liang and Don Metzler, just search CIIR talk series in YouTube and find those presentations. Leif's presentation will be uploaded too. And the next presentation in 2 weeks from now will be from Evangelos Kanoulas from University of Amsterdam. He will be talking about conversations and sessions and their relationships. And yeah, that's it. Thanks for being here. And Leif, please join the other Zoom link for the meetings.